Hello and welcome to part 2 of Bitcoin transactions in depth. Now we'll be discussing how we go from tentative transactions to tentative blocks to ideally new blocks. So we'll start off right where we left off. So in the previous video we created a tentative transaction 1 and we broadcasted this tentative transaction 1 to the Bitcoin network. Now what we can assume is during a 10-minute interval, you know, the amount of time where we expect a block to be, put together and created, miners will be compiling a whole bunch of other tentative transactions. So what miners will do is they'll look at all these tentative transactions, so 2, 3, 4, 5, etc. We'll look at each and every single one of these transactions and determine whether or not these transactions are valid, whether or not these transactions are double spending, whether or not these transactions have proper authorization. Now, assuming all of these transactions are indeed valid, what miners will start to do is they will start to hash pairs of tentative transactions together to once again condense data and to create a sort of a hyperlink of sorts to the individual transactions data. So for example, you can look at the hash of transaction 1 and transaction 2, which is right here. It's important to note these are digests. These aren't just two transactions in one. These are digests. And I'll say that right here so that there's no confusion. But what we're looking at are indeed the outputs of hashing functions. But in any case, this digest right here, if you follow this hash, it will take you back to these two independent transactions where you can look at the transactional details in more depth. But what miners will do is they'll start condensing this information, compiling transactions, pairs of transactions, over and over and over again during this 10-minute interval until they create what is known as a tentative block. So this is a tentative block of, approximately 2,000 transactions. So as you can see, I don't have enough space to draw 2,000, so just sort of, so bear with the horrible visual aid here, but essentially tentative blocks have about 2,000 transactions. When segregated witness passes, this will increase to about 4,000 to 5,000 transactions per block. But here's the interesting part when it comes to miners in the proof of work algorithm. This is where the mathematical puzzle comes in, and this is where the vast amount of required computational power come in to play. So in order to make this tentative block a real block and to add it to the Bitcoin blockchain, you have to solve a puzzle. And it's a puzzle that you cannot solve analytically. There's no shortcuts. There's no clever way of doing it. The only way you can solve the proof of work algorithm is you have to brute force it. You have to try as many different possible values of the solution as possible until you get one that actually satisfies the problem. So I just want to mention that right here, right now. There's no clever way of doing this. There's no clever way of outsmarting the proof of work algorithm. It is designed specifically to be a computationally intensive brute force method. You cannot do it any other way. So to get back to what I was saying, for the proof of work algorithm, we want to find a nonce. That's a very, very fancy way of saying we want to find a number. If this number could be anything. There's no specifications to this number. So this could be a 1-digit number. This could be a 5 billion digit number. There's no requirement here. But essentially, we're looking for a nonce or a number such that when we take the hash, the SHA-256 hash of this tentative block here, and we add the nonce to this tentative block. So you can think of it as whatever numbers represent this tentative block, we attach to the end of whatever those numbers, we attach the nonce to it. When we take the hash of both of those things put together, we want to get something. We want to get an output that is less than or equal to D, where D is a difficulty target. Now, as I mentioned in other videos, Bitcoin's supply is self-calibrating in the sense that if miners are creating new blocks too quickly, what the system will do is it will adjust the difficulty of the proof of work algorithm. the way that they do this is they increase the number of required zeros in the difficulty target. So let me pause for a second and just explain this more detail right now. So let's suppose for D right here, D is the average. D is about 40 zeros. So it's 40 zeros. So what that means is D is equal to a number that is equal to 0.000, 40 zeros follow that decimal point, 40 leading zeros. And then after that 40th leading zero here, and I'll designate this as the 40th zero. After this 40th zero, it could be, it really doesn't matter. We don't care what comes after this 40th digit. We honestly don't care. It could be whatever you want. It could be zeros, ones, nines, sevens, who cares? But essentially, this is how the difficulty target is set up. This is how the proof of work algorithm is set up. You want to find a solution to where the output of the SHA-256 of the tentative blocks plus the nonce is less than D. And to go back to what I was saying earlier, if miners happen to be creating blocks too quickly, and this could be due to just randomness, because there's a huge element of randomness when it comes to the proof of work algorithm, because on average we expect you to do about 30 quintillion computations per block. We expect that, but sometimes you might do that in half the amount of work, sometimes you might do that in twice the amount of work, for no other reason other than just randomness. So let's say in the event that miners were making blocks too quickly due to randomness, or maybe hardware has improved to the point to where they can create or compute those 30 expected quintillion computations faster than normal. So what the system will do is it will increase the difficulty targeting by adding an additional zero. And by adding this additional zero, so let's say going from the average that we just stated of 40 leading zeros to a difficulty target of 41 leading zeros, what that does is that doubles the expected amount of computations to solve the proof of work algorithm. Now vice versa, since it's self-calibrating and calibration goes both ways, in the event that miners were not creating blocks fast enough, they weren't creating blocks in 10 minutes, maybe they were taking 13 minutes, and we all know that Satoshi wants it to be 10 minutes to fit into the long-term supply curve. What we'll do is we'll decrease the required amount of leading zeros. So maybe the average amount is D, we go from that and we make it 39 leading zeros. And what that will effectively do is that we'll have the expected amount of computations to solve the proof of work algorithm. But really, that's all there is to the proof of work algorithm. It just requires miners to just try as many different possible values of this nonce, which, like I said, there's no specification on that. They can be whatever you want. You could do that however you want, but basically it comes down to trying as many different values of the nonce as fast as possible until you get an output of the tentative blocks plus nonce's digest that's less than D. And by less than D, all I mean is that the output has more leading zeros than what is required by, or at least the same amount of leading zeros as required by the difficulty targeting. That's what I mean. So a lot of people get mixed up with this when it comes to understanding what do you mean by taking the hash of a tentative block and a nonce. At this point, it's important to remember that a hash function takes whatever kind of data you give to it, and it spits out an output. So even though you might think this block might not really technically be a number, and you can't just add a number to a tentative block, it's all data. Whatever data makes up this tentative block can be hashed with the nonce to give an output that can be less than, equal to, or greater than the difficulty. Now before I end this video, I want to discuss what would happen if two miners or two different pools found a solution to the proof of work algorithm simultaneously. Now one thing that could happen is you could have a miner in Australia come up with a solution at the exact same time as a mining pool in the US comes up with a solution. So they both find the solution at the same time from a global perspective, but the thing is they're located in two different parts of the network. What that means is all the nodes that are located near Australia are going to receive Australia's solution first, and all the nodes near the US are going to receive the US's solution first. Now, what's going to happen in the event that that happens is you're going to have two different solutions to this particular block. Let's say this is block 5000 on the blockchain. We call this a split in the chain. And what's going to happen is the nodes that receive this Australian solution are going to immediately begin to start working on the new node, the next node that follows this solution. And it's going to be the same thing over in the US. The nodes are going to immediately begin working on the next block. Now what's going to happen is, let's say for example, we're thinking about nodes in Australia. Now as the solution from the US reaches over to Australia, what's going to happen is the cumulative difficulty between the blockchain using solution 1 and all the previous blocks will be compared to the cumulative difficulty of solution 2, or the US's solution, with all the preceding blocks. So let me write that down. The cumulative difficulty is going to be the tiebreaker in this situation. So let's say, for example, the US solution has a higher cumulative difficulty than the Australian solution. So just to repeat what I said, when this solution goes over to Australia, the nodes are going to compare the cumulative difficulties and they're going to choose the US solution. And what's going to happen is when they choose the US solution, they're going to forget the Australian solution and whatever subsequent block they were trying to work on or they were starting to work on. These blocks over here become orphan blocks. Now the important thing to know about orphan blocks is that if your transaction was on an orphan block and your block gets orphaned, your transaction doesn't go through. So you'll have to wait until your transaction gets picked up by another miner once again, and they put it into a tentative block, and they solve the solution for that block. That's only then will your transaction actually be fulfilled. But just a brief recap, we discussed the process by which we go from individual transactions, and miners compile these individual transactions, assuming they're valid, into a tentative block. Once they have a tentative block, they try to find a nonce or some number, random number, such that when they take the SHA-256 hash of the tentative block and the nonce, they get an output with less or more, equal to or more than 40 leading zeros, or D leading zeros. In our example, we assume that difficulty was an average difficulty, which is 40 zeros. So to repeat what I said, we're looking for a nonce such that the hash of the tentative block and the nonce has greater than or equal to 40 leading zeros, or D leading zeros. In the event that two miners come up with solutions at the same time on different parts of the globe, whichever solution wins out is determined by the cumulative difficulty of their solution with all the preceding blocks before it.